right, let's move on to chapter 10 in your textbook, alkenes. All right, first some general stuff about alkenes. If the alkene exists at the end of the molecule, we call it a terminal alkene. If it's somewhere in the middle, it's an internal. Of course, if it's in the middle of the ring, it's a cycloalkene. A few things to remember, hopefully you do, that a double bond of an alkene consists of a sigma bond between the two carbons and a pi bond between the two carbons. If you look on tables, you'll find out that the strength of these two bonds together is 635 kilojoules per mole. A carbon-carbon single bond, typical carbon-carbon single bond, has a strength of 368 kilojoules per mole. Just doing a little quick math, looking at the two, that tells us that if the sigma bond is 368, the pi bond must be 267 kilojoules per mole to get this total for the double bond, which means pi bonds are less stable than sigma bonds. Therefore, if you've got an alkene and you go to break that bond, the pi bond is weaker. The pi bond will break first. Okay. And if you get your models out and you give it a go, you will find that small cycloalkanes, they have to be cis. You note if you have this cyclohexene up here, you cannot have it trans. If you had this carbon going to this carbon over here, then had a double bond, if it was trans, so the rest of the ring came out that way, there's no way to attach those two back together in 3 carbon and 3 CH2s. All right, so they are going to be cis double bonds in cycloalkenes. The largest trans cycloalkene we have is trans cyclooctene, but it's very unstable because that's barely enough carbons to connect the two ends of a trans alkene together in a cyclic fashion. All right. So, when you have rings or double bonds or triple bonds in your molecule, we can calculate what we call the degree of unsaturation. Hopefully you will not need your calculator for these calculations, but who knows. Note on the final exam, you will not be able to use your calculator. On any of our exams, we can't use your calculator, so hopefully you can do this second grade math in your head. You will find that you might not be able to. All right, so anytime you have an alkane, recall that as CnNH2n plus 2. All right, so if you have 5 carbons your alkane, you're going to have 12 hydrogens. If you have an alkene, in order to form this carbon-carbon double bond, that means we've got a CH3, CH, CH, CH2, CH3. These two carbons are now CHs, whereas they used to be CH2s. We have gotten rid of 2 hydrogens to make that double bond. So an alkene is CnH2n. We've gotten rid of the plus 2. So we're going to call that 1 degree of unsaturation. A saturated hydrocarbon, all carbon-carbon bonds are single bonds, which means that molecule contains as many hydrogens as is capable of having. All right, note if you did a cyclopentane, the formula for cyclopentane is C5H10 because it's H2, 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 H2. So note it also has 1 degree of saturation. A ring, to make a ring, we have to add an extra carbon-carbon bond because essentially we would have taken this carbon here and bonded it to that one. We've got another carbon-carbon bond in there. We got rid of 2 hydrogens. So an alkene is 1 degree of saturation. A double bond, that pi bond gives us 1 degree of saturation. A ring gives us 1 degree of saturation. A carbon-oxygen double bond is 1 degree of saturation. Of unsaturation, excuse me. What would a carbon-carbon triple bond give us? Well, carbon-carbon triple bond has 2 pi bonds. That is 2 degrees of unsaturation. Well, here's a question. What about a benzene ring? How many degrees of unsaturation is that? Well, just by looking at it, we can see, all right, we've got 1, 2, 3, 3 double bonds. That's 3 pi bonds. That'll give us 3 degrees of unsaturation. And we've got a ring. So that's another degree. That are 4 degrees. A benzene ring has 4 degrees of unsaturation, which means a benzene ring is missing 4 H2 molecules compared to a normal straight chain 6-carbon alkane. And that's easy to figure out. We can just look, the benzene ring is C6H6. What is normal straight chain hexane? C6H1214. Ooh. A normal hexane would have 14 hydrogens. Benzene has 6. 14 minus 6 is, what's 14 minus 6? Good heavens. 14, 13, 12, 11, 10, 9, 8. So, yeah, so 14 minus 6, there's a difference of 8 hydrogens. 8 hydrogens is 4 H2 molecules. Degree of unsaturation is 4. All right, so now some people laugh at me when I count hydrogens and electrons that way. Guess what? It works for me, and when I do it that way, especially counting electrons to actually physically count them, I don't mess up on exams. Yay, yay for me. All right, so that's fine and dandy, but what does this knowledge tell us? Well, the nice thing is you can actually calculate the degrees of unsaturation in a molecule if you just know its molecular formula. So we're going to find this is especially beneficial with NMR problems. Anytime you're trying to figure out the structure of your molecule, if you have its formula, you can actually calculate the degrees of unsaturation. That'll give you a little extra knowledge. All right, prime example, if you have the formula for a molecule and you take an IR of it, and you note that, okay, my molecule has 1 degree of unsaturation, but you note that there are no peaks at around 3,100 wave numbers, which means there are no carbon-carbon double bonds. Well, how can a molecule have a 1 degree of unsaturation with no carbon-carbon double bonds in it? It's a ring. That's figuring out if your molecule is a ring or not is often difficult to do, but if you have the degrees of unsaturation of 1 but no indication of carbon-carbon double bond, that tells you that you do have a ring. So that might be nice. And so here's the formula. Note, different books have different formulas. Don't mix them up. Use my formula of how to calculate the degrees of unsaturation. The degrees of unsaturation will be the number of carbon atoms minus 1/2 the number of hydrogen atoms minus 1/2 the number of halogen atoms, X stands for halogen, plus 1/2 the number of nitrogen atoms, plus 1. And this works for almost every molecule. If your molecule has oxygen, sulfurs, phosphorus actually go under this because they're the same as nitrogen, but oxygen, sulfur, halogens, note there's no oxygen in this formula because we don't worry about it. The oxygen isn't involved in the degrees of unsaturation. Even if it's a double bond to the oxygen, it's not in the formula for determining it. So this formula works on almost any molecule you will come into contact with. So let's do this first. First, let's look at this molecule. We can tell it's got 1 double bond. It should have a degree of unsaturation of 1. So let's just make sure. Number of carbons, 4. Number of hydrogens, well, 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogens. So that's 1, subtract 1/2 of 8. What's 1/2 of 8? Well, that's 4. No halogens, no nitrogens. So they need to add our 1 there. So it's 4, number of carbons, minus 1/2 the number of hydrogens, plus 1. 4 minus 1/2 of 8. Well, half of 8 is 4. 4 minus 4 is 0. 0 plus 1 is 1. Yay! It works. All right. Okay, let's look at this molecule right here. We can see it's got a ring and a double bond. We're expecting 2 degrees of unsaturation. 6 carbons minus, well, how many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9. 6 carbons minus 9, 1/2 of 9 hydrogens. We've got 1 chlorine, so we've got to subtract 1/2 of 1 for chlorine, plus 1. Now here's where the problem is, because your brain is going to want to do something very bad. It's going to want to simplify this. You're going to see, oh, 1/2 of 9 and 1/2 of 1, that's 9 halves and 1/2. And you're going to be like, oh, well, what's 9 halves minus 1/2? Oh, 9 halves minus 1/2 is 8 halves. And so it takes 6 minus 8 halves. Well, 8 halves is 4. 6 minus 4 is 2. 2 plus 1 is 3. But the answer is 2. Because your brain did something wrong. In an effort to simplify this part right here, in an effort to get rid of your 9 halves fraction and your 1/2 fraction, you subtracted this from here, but then you subtracted this from it, subtracted the combo from here, and that's not how you do it. You have to go in order. Don't try to combine steps. You have to go in order. 6 minus 1/2 of 9, well, that's 4.5. So 6 minus 4.5 minus 0.5. So that's 6 minus 4.5 minus 0.5 is 1. 1 plus 1 is 2. Don't combine these together to try to simplify it. Your brain wants to do that. Don't let it do it. All right, but these examples are fairly obvious, straightforward. Where you're really going to find out is, okay, here's C8H9N. You've got the formula for your compound. The question is, what's its degrees of unsaturation? When given a formula, okay, now we're cooking. 8 carbons. We've got 9 hydrogens minus 1/2 of 9, so we know that's 4.5. So we're at 8 minus 4.5 is 3.5. We've got 1 nitrogen, so we have to add 1/2 of nitrogen, so we're at 3.5 plus 1/2 is 4, plus our 1 is 5. 5 degrees of unsaturation. C8H9N has 5 degrees of unsaturation. Note, it doesn't tell us where we have how many rings or double bonds or whatever. We just know we have 5 degrees of unsaturation. Turns out that this is the molecule. This is an example of C8H9N with 5 degrees of unsaturation. Note, just getting 5 degrees unsaturation doesn't say, oh, it has to be this. It's just like, well, how do I get this molecule with 5 degrees of unsaturation? That is one way to do it. It'll help narrow down the possibilities of what molecules we have. All right. So, nomenclature. Good news, we've already done nomenclature of alkenes. We know what's going on here. So, that's not a problem with hexenes and 1-methylcyclopentene and all that stuff. Recall that if you have a double bond and an alcohol in your molecule, that it's always the carbon containing the OH gets the lowest number possible. Even though this alkene is way down here at the end, this is the end of the molecule. It starts carbon 1 here so that the carbon containing the OH can be carbon 2. So this is 6-methyl 6-heptene 2-all. Barf. All right. Recall with alkenes we have stereoisomers, specifically diastereomers. Cis and trans are diastereomers. And recall when we're deciding whether it's cis or trans, we need to look at the hydrogens and we say, okay, we didn't draw it here, but yes, there's a hydrogen up here and a hydrogen coming down here. And cis versus trans, we draw a line through the bond. The hydrogens are on opposite sides. Therefore, that is the trans isomer, trans 2-pentene. And when we look at this one here, our hydrogens are on the same side, so that is the cis. Here's the problem. What do you do with this molecule? How are we going to name that? Well, we have a problem in that we only have one hydrogen. Only one hydrogen right here. There's no hydrogens on that carbon. So you cannot have the words cis or trans, you cannot have that as part of the name, unless you have two hydrogens. Now, we can always use cis and trans as relative position. We can always say, oh, check this out. The methyl group on this side is cis to the methyl group on the other side of the bond. Yeah, these two methyl groups are cis to each other. We can say that, but we can't name this the cis molecule. We can't have cis in the name, because if cis is in the name, that means we have to have two hydrogens cis to each other. So we need a new naming system on how to name these molecules, and don't worry, it's not difficult. It is the EZ system. Okay. Good news, easy system, not a whole lot else to remember. We just have to recall good old Kahn-Ingold-Prelog rules for naming R and S. But we're not even going to go that difficult. We're just going to say, hey, remember priorities? Remember how we assigned priority 1 to the atom with the largest atomic number, and priority 2 is the next largest, and stuff like that? We're just going to do that for each side of the molecule. So if we look at this molecule right here, where we have the CH3 and the CH3 cis to each other on this double bond, it's essentially this molecule there, we can say, all right, look at this carbon. What's coming off of it? Well, a methyl's coming off it and a hydrogen. What is higher priority using Kahn-Ingold-Prelog rules? Well, carbon is higher priority than hydrogen. So this is priority 1 and this is priority 2. Then we go to the other carbon on the other side of the double bond. And look at that. And we say, okay, here we have an ethyl and here's a methyl group. Which is higher priority using Kahn-Ingold-Prelog rules? Well, they're both carbons. So remember, okay, so then we have to go next out. Well, this is HHH, whereas this is CHH. So we know that our longer chain here has higher priority. This is priority 1. This is priority 2. All right. Then we do the same thing we would have done for cis and trans. We draw a line along the double bond. And then we look for our two priority 1s. Note our priority 1s are on opposite sides of that line. Our priority 1s are trans to each other. If our priority 1s are on opposite sides, then that is the E isomer. Note if we look at this isomer here, our methyl is priority 1 on this carbon, our methyl is priority 2 on this carbon. Note our priority 1s are on the same side. They're on the same side of the line. That is the Z isomer. Now, here's the deal. The biggest problem with E and Z is I'm basically asked, oh, is this the E isomer or the Z isomer? And you're going to look at it and say, okay, priority 1s, they're on the same side, and that, oh crap, is the same side E or is the same side Z? How am I going to remember that? And you're going to try to come up with some trick to remember which is E and which is Z, and hopefully you'll have a good one, but if you can't, you can use the trick I came up with. And the thing to remember, anytime you have to remember two things, one is this way and one is that way, the best way to remember it is some sort of stupid saying or some sort of really stupid thing, because you just remember the stupid stuff. Okay, here is Watson's stupid way of remembering E and Z isomer. You can use your own way, but this is how I do it. The Z isomer has priority 1s on the same side. That's how I say it. Z, same side. E, opposite sides. How dumb is that? Oh, it's exceedingly juvenile. Yes, but that's how I remember it. Oh, our priority 1s are on E, opposite sides. Oh, opposite sides. E. Oh, priority 1s are on the same side. Oh, the same side. Same side is Z. That's how I do it. I kid you not, you'll be in Organic 2 next semester. Your instructor will be like looking at these and say, oh, is this the E or the Z isomer? And you're just going to smack your head against the desk and look like, oh man, that's the Z isomer because priority 1s are on the same side. It's a way to remember it. That's what I'd recommend. Okay, let's finish up this video with a few examples. Let's look at this molecule right here. Is this the E or the Z isomer? Okay. Well, look at our two carbons. Here's priority 1, methyl's priority over hydrogen. What if we have a chlorine and a bromine? Well, bromine has a higher atomic number than chlorine, so bromine is priority 1. Draw a line going this way through it. We see that the two priority ones are on the opposite sides. One is here, one is here. So this is the E isomer. Yeah. All right. Actually, before we go, one last thing, just so we can put in our heads. Anytime you have a CH2, a terminal alkene, where you have a CH2 double bond CH to something, terminal alkene is called a vinyl group. We call that vinyl. If you have a terminal, this is a vinyl group here, but you have a CH2 attached to it or another carbon attached to it, this 3-carbon group of an alkene is called an allyl group. So the 2-carbon group of the alkene is the vinyl group. The 3-carbon group of the alkene is the allyl group. All right, that's enough for this video.